After completing this lesson, you should be able to describe and analyze the operation of common emitter amplifiers. Describe a common emitter amplifier with voltage divider bias, show its input and output signals, discuss phase inversion between output and input voltages. You will represent the amplifier by its DC equivalent circuit and perform DC analysis. To perform the AC analysis, you will represent the amplifier by its AC equivalent circuit and you will define a C ground. This is a common emitter amplifier with voltage divider bias and coupling capacitors C1 and C3 on the input and output, and a bypass capacitor C2 from emitter to ground. The input signal Vin is capacitively coupled to the base terminal. The output signal Vout is capacitively coupled from the collector to the load. The amplified output is 180 degrees out of phase with the input, because the AC signal is applied to the base terminal as the input and taken from the collector terminal as the output. The emitter is common to both the input and output signals. There is no signal at the emitter because the bypass capacitor effectively shorts the emitter to ground at the signal frequency. All amplifiers have a combination of both a C and DC operation which must be considered, but keep in mind that the common emitter designation refers to the AC operation. The output signal is 180 degrees out of phase with the input signal. As the input signal voltage changes, it causes the AC base current to change, resulting in a change in the collector current from its Q point value. If the base current increases, the collector current increases above its Q point value, causing an increase in the voltage drop across the collector resistor RC. This increase in the voltage across RC means that the voltage at the collector decreases from its Q point. So any change in input signal voltage results in an opposite change in collector signal voltage, which is a phase inversion. To analyze the amplifier, the DC bias values must first be determined. To do this, a DC equivalent circuit is developed by removing the coupling and bypass capacitors because they offer infinite reactance to DC and hence appear open as far as the DC bias is concerned. Hence, this DC equivalent circuit does not include the load resistor and signal source because they are isolated from the amplifier circuit due to the infinite reactance of the capacitors. After determining the Thevenin equivalent circuit for the bias circuit, we find the Thevenin resistance to be 5.19 kilo ohms and the Thevenin voltage to be 2.83 volts. Applying Kirchhoff's voltage law to the base emitter circuit, we find that the emitter current is 3.58 milliampere. The emitter current is approximately equal to the collector current and hence the emitter current is taken as 3.58 milliamperes. The emitter voltage is 2 volts. The base voltage is emitter resistor voltage drop plus the diode forward voltage drop. It is 2.7 volts. The collector voltage is supply voltage minus the collector resistor voltage drop, and it is 8.42 volts. Voltage VCE is 6.42 volts. This completes the DC analysis in which we have determined all the DC voltage and current values. To analyze the AC signal operation of an amplifier, an AC equivalent circuit is developed. It is a two-step procedure. First, the capacitors C1, C2 and C3 are replaced by effective shorts because their values are selected so that their reactance is negligible at the signal frequency and can be considered to be 0 ohms. Second, the DC source is replaced by ground. An ideal DC voltage source has an internal resistance of 0 ohms because it holds a constant voltage independent of the load. thus no voltage variation can be developed across it. So, it appears as an AC short. This is why a DC source is called an AC ground. In the AC equivalent circuit for the common emitter amplifier, notice that both RC and R1 have one end connected to a C ground, shown red because in the actual circuit they are connected to VCC, which is in effect a C ground. In AC analysis, the AC ground and the actual ground are treated as the same point electrically. The amplifier is called a common emitter amplifier because the bypass capacitor C2 keeps the emitter at a C ground. Ground is the common point in the circuit. An AC voltage source Vs is shown connected to the amplifier input. If the internal resistance of the AC source is 0 ohms, then all of the source voltage appears at the base terminal. If, however, the AC source has a non-zero internal resistance, then three factors must be taken into account in determining the actual signal voltage at the base. These are the source resistance, Rs the bias resistance, R1 in parallel with R2, and the AC input resistance at the base of the transistor, R in base. In this lesson, we have understood how to develop the DC equivalent circuit of a common emitter amplifier and perform DC analysis. We have also learned to develop the AC equivalent circuit. In the next lesson, we will perform a C analysis, develop expressions for voltage gain, current gain and power gain.